All right. First two paragraphs that we're going to get after this. We'll watch a couple short YouTube videos. Real short. Okay? First two paragraphs there. Everybody there?
What page?
287. Okay. It says, it is probably fair to say that at the end of the 19th century, physicists were feeling rather smug. Theories could explain phenomena as diverse as the motion of the planets and the dispersion of visible light by a prism. Rumor had it that students were being discouraged from pursuing physics as a career because it was felt that all the major problems had been solved. It's funny, isn't it? Or at least described in terms of the current physical theories. At the end of the 19th century, the idea prevailed that matter and energy were distinct. Matter was thought to consist of particles, whereas energy in the form of light was described as a wave. Particles were things that had mass and whose position in space could be specified. Waves were described as massless and delocalized, that is, their position in space could not be specified. It also was assumed that there was no intermingling of matter and light. Everything known before the 1900s seemed to fit neatly into this view. Until a guy by the name of Max Planck came around. I wasn't planning on reading the next paragraph. Let's read the next one and we'll be done. At the beginning of the 20th century, however, certain experimental results suggested that this picture was incorrect. The first important advance came in 1900 from the German physicist Max Planck. Studying the radiation profiles emitted from solid bodies heated to incandescence, Planck found that the results could not be explained in terms of the physics of his day, which held that matter could absorb or emit any quantity of energy. Did everybody catch that? Reread that phrase. That was probably the big thing here. Matter could absorb or emit any quantity of energy. Okay? Basically, they believed that energy was continuous. It just could flow without needing specific parameters. It just flowed regardless of how much or how little it had. Planck could account for these observations only by postulating that energy can be gained or lost only in whole number multiples of a quantity, hv, where h is a constant that he came up with, determined from experiment. That is, the change of energy for a system can be represented by an equation. I'll read the very last paragraph before the energy of a photon, and then we'll talk. Planck's result was a real surprise. It had always been assumed that energy of matter was continuous, which meant that the transfer of any quantity of energy was possible. Now it seemed clear that energy is in fact quantized and can occur only in discrete units of size. Each of these small packets of energy is called a quantum. So, essentially what he found out was this idea of quantization, which means that energy can only be absorbed or released in certain packets of energy. Okay? There is a smallest form of energy that can be released. You cannot get any smaller than that particular form, and it always gets transferred in some whole number multiple of that little packet. So like if I wanted to give you energy, I could only give you a packet or a multiple of that packet of energy. I could not give anywhere in between that multiple. Okay? I know that seems really, really weird. You're probably like, oh, how does that play into the bigger scheme of things? We'll get to that. Okay? But I couldn't just stream energy to you at will. Okay? It really gets passed through packets of energy, which they call a quantum, and this phenomenon is called the quantization of energy. Okay? Now, with that being said, let's try to figure this out with a couple mathematic problems. And we'll continue on with this idea of quantization. Okay, it says the blue color of fireworks is often achieved by heating copper chloride really hot. Okay? This emits a blue light of wavelength 450 nanometers. What is the increment of energy, the quantum, that is emitted? The packet of energy that gets emitted. It's not an infamous, instant, continuous stream of energy. It's given off in discrete packets of energy. Let's figure out how much energy that would be. You guys have the equation, right? E, change in E equals Planck's constant times the wavelength. That's my bad marker. Where are my good markers? There it is. Now I'm not going to make you memorize Planck's constant, although you might after using it enough. Oh, sweet. Thanks, Titus. I think I go through more markers than anybody. Maybe not Merriman.
He uses a smartboard.
Okay, yes, I do go through more. I should get a smartboard. They should give me a smartboard.
Actually, his pens are more expensive because those things die.
Pens die?
Like the inch. No, well, no, he puts batteries in, but they break really easy, and they only last like 2 or 3 months.
He said one last week.
Oh, really?
Yeah, this one's last week.
That's good. Last year's went through 2. Maybe more than 2 or 3 months, but.
Okay, so there's your Planck's constant. They gave you a wavelength, 450 nanometers, and they want you to find the change in E. How do we go about solving this particular problem? It appears that we don't have the variable we need, the variables we need. What is what?
Use
Frequency.
So you
the
solve.
frequency and speed of light.
So you're going to use the speed of light equation to find the frequency because they gave you the what? Wavelength. Because remember, if we know the wavelength, we should be able to find the frequency because they go hand in hand. High wavelength means what for frequency? Low. Low wavelength means high frequency. So why don't you guys use the speed of light equation to figure out what frequency we would have to put in here to get particular amount of energy. And we'll talk about how we have to meet a certain frequency threshold, otherwise these packets of energy being emitted won't happen. Need it in meters. What do we get? First of all, what do we get for frequency?
6.6 times 10 to the
That's the total answer?
No. Oh, yeah, sorry. That's speed.
Okay. So it's going to be in hertz. Okay, then we're going to take that and we're going to plug it into our energy, which a hertz is an inverse second, so that will cancel out with our seconds here and give us joules.
For our study session, I should bring her studies.
Well, you could most definitely bring the good ones though.
Didn't do it.
I've never had them.
Okay, I'll try.
Okay, so we've got Planck's constant, and it's I don't even remember. I've been doing this for a while. I don't even remember this number. I don't have it memorized.
6.66.
I'm gonna put this in inverse second form so that we can see how we're gonna get our joules out of it. What was our final answer?
4.4 times 10 to the negative 19.
4.41 times 10 to the negative 19 joules. Okay? What this simply means is that when this blue light is emitted, it is emitted in small packets of particles known as photons that have that much energy. And that is a whole number multiple of what Mr. Planck discovered was the smallest packet you could have. Okay, it wasn't a stream of particles, it's a stream of packets. If that makes sense. I know it's deep.
Like bursts of energy, those tiny ones.
Yeah, it's just like pop, 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 and it's all these little packets of energy that's getting streamed instead of a continuous. So imagine like energy flowing, that direction with little packets versus just looking like that. Does that make sense? Okay, it's a flow of packets of energy, not a continuous stream. Okay, which is interesting. We're going to get in a little bit deeper into this as we continue on. We haven't even talked about Einstein yet. We're about to. Okay, Mr. Albert. Okay, the next important development in the atomic structure came from Mr. Albert Einstein. He proposed that light was quantized as well. Okay, well, up to this point, everyone believed that light acted like a wave. Okay, and there was evidence to support that it acted like a wave. Okay, he suggested that electromagnetic radiation can be viewed as a stream of photons, or like I said, a stream of small packets, and those packets would be described as photons. Okay? He came up with this equation. The energy, or the smallest, this would be your small packet of energy from your quantization, that would be the energy of a particular photon, was dependent upon Planck's constant. This is essentially what we just did, but you see how they added the the speed of light equation in here to replace frequency if we didn't have frequency. Okay, we just knew the wavelength. Because typically when we talk about light, we talk about it in its wavelength. We usually don't talk about it in its frequency. Right? When you talk about the Roy G. Biv spectrum of light, we usually talk about it, not a Roy B. Did I say that wrong?
No, you
I
didn't.
just wanted to settle.
Okay. They usually give it in the wavelength. They don't typically give you it in frequency. Okay? Now, I do want to then talk about how we discovered this, which this is a lot. Right? So, let's look at the photoelectric effect on page 289. Everybody get there. This is what he won the Nobel Peace Prize for. He actually won it for the photoelectric effect. He didn't win the Nobel Peace Prize from Nobel Peace.
Nobel Priest.
So he won it. He won his Nobel Prize for the photoelectric effect, not for his E equals mc squared equation, which is kind of interesting. Okay? So, let's see here. Let's look at his photoelectric effect here. It says, Einstein arrived at his conclusion, so the conclusion about this energy, electromagnetic energy, is quantized as well. Through his analysis of the photoelectric effect. The photoelectric effect refers to a phenomenon in which electrons are emitted from the surface of a metal when light strikes it. Okay? Here's what he observed. Okay, his studies in which the frequency of light is varied show that no electrons are emitted by a given metal below a specific frequency threshold. Which means, as he was shooting light at the surface, at a metal surface, below a specific frequency, no electrons got emitted off the surface. There wasn't enough energy for it to get emitted. It didn't have enough packets of energy to allow it to emit a packet of electrons. Or a packet of an electron. Okay? For light with frequency lower than the threshold frequency, no electrons are emitted, no matter how intense the light. So they could have just an outrageous amount of light, but if it was below a particular frequency, no energy got emitted in the form of an electron. For light with frequency greater than the threshold frequency, the number of electrons emitted increased with the intensity of light. So as soon as they got over the fundamental threshold frequency, as the light got intense, so did the amount of electrons emitted. Right? For light with frequency greater than the threshold frequency, the kinetic energy of the electrons increased linearly with the frequency of light. So not only did, after they got over the threshold, did the amount of electrons get emitted increase with intensity, but also the higher the frequency, the more electrons that got emitted was as well. So this led to a couple equations. Right? The kinetic energy of the electron getting emitted from light hitting the surface was based on this, or probably more importantly, this is your threshold frequency. So the amount of kinetic energy that was released was based upon how much your frequency was above the threshold. If it wasn't above the threshold, no energy, no electron even got emitted. Okay? Now I'm going to show you a couple videos here to kind of continue to explain for us what exactly this meant for modern physics. And I'm going to move this so I don't have copyright issues. I did that on one video, and YouTube's like, you have copyrighted somebody else's video.
Copyright, it's an automatic thing. Copyright strikes so quickly.
Let's start with this one.
Knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also wrote, I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down
Those equations.
until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave. sometimes as a particle and sometimes as either. It was a revolutionary
Mind blown.
and it opened the field for quantum physics.
Schrodinger's cat.
Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So, he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Alright, one more.
Is the cat dead? Or is it alive? You poisoned it. You can see it's going out.
As an electromagnetic wave. For this reason, light is also called electromagnetic radiation. Light waves have both a wavelength, the distance from tip to tip, and a frequency, the number of waves
We
that
know
pass
this already.
by
Come on.
per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency.
It looks like a Russell.
These variables are related by the following equation, in which c is the speed of light, about 300 million meters per second, the speed limit of the universe. The electromagnetic spectrum shows light at all the different wavelengths, from gamma rays to radio waves, including this tiny sliver in the middle, which is visible light, the light we can detect with our eyeballs. The wave theory of light was very useful for a time, but it could not explain the photoelectric effect. This was the observation that if a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or plate sensor. The incongruity was that the ability of the light to eject an electron depends only on its frequency and not its intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron, whereas above a certain frequency, the faintest beam possible could do it. This seemed strange, and a famous fellow named Albert Einstein solved the problem by extending a concept developed by Max Planck just 5 years prior. Planck proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of the smallest fundamental unit of energy, the Planck energy. In fact, quantum theory went on to show that everything is quantized, space and time too. So you can't infinitely subdivide them. You'll eventually get to a smallest thing that can't be divided further. But more on that in the physics course. Einstein extended what Planck said about energy and rationalized that light must also be made of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above a certain frequency will be able to do it. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy of a photon can be given by the following equation according to the frequency of the photon and Planck's constant. We now have to accept that light obeys wave-particle duality, meaning it is both a particle and a wave at the same time. Confused? You should be. This is the first discovery in a series that brought about the quantum revolution, completely changing the landscape of physics and how we view the universe. Newton's laws no longer reign supreme in the world of the very small, and the universe became much stranger almost overnight, thanks to Einstein and others that were inspired by him. Thanks for watching, guys. Subscribe to my channel.
Alright. So, over our heads, a little bit. It's a lot. I totally understand what I've just thrown at you is kind of a lot. What I really want you to grasp out of this more than anything is this idea that everything is quantized, which I think is interesting because if you can say that everything comes down to some smallest form, okay, so they say that you cannot subdivide energy any further than the smallest form. I think that leads to there was a specific creator that God designed this specific world a specific way. Right? That there's an actual smallest thing. Okay? And it just doesn't continually be subdivided forever. Okay? As we're continuing on here, you probably then are at least familiar with his Einstein's theory of relativity, which is E equals mc squared. What was the big hurrah about that equation? Why is that an equation that is so praised more than anything, I feel like?
Because people don't know what it is, but it makes it fancy.
Yeah, sure. It's actually it's not a really big equation. The thing that really got people all up in arms was that, well, we know what that is, so what is this? Mass. And here's what got everybody up in arms about, was that energy has mass.
I didn't even know it was happening. I was waiting for that. I've been waiting for that this whole entire life.
Energy has mass. Really? But it's not mass like we think. Okay? Believe it or not, a photon behaves as if it has mass only under certain circumstances. It doesn't have mass all the time, which is interesting.
That doesn't make sense.
I know, right? Okay? A guy by the name of Arthur Compton performed experiments involving collisions of X-rays with electrons that show that photons do exhibit some apparent mass calculated from an equation. However, it's clear that photons do not have mass from its classical sense. It is more that it has a relative mass. And what that simply means is it doesn't have rest mass. It only has mass when it's moving, which is interesting. Okay? This is really what is summed up by the wave-particle duality. Okay? So here is a few other equations that we can use. We can find the mass or the apparent mass of a photon that has wave and particle properties with that equation. Okay? And then we can use de Broglie's equation to figure out this relationship with speed. Okay? Alright, I realize this is a whole lot of stuff. Let's summarize. This is really the big thing that I want you guys to walk away from. Do I expect you guys, this is really the first time we've really started to hammer into the wave-particle duality, the idea of quantization of energy. Like, this is the first time you see it, and this is probably the lowest level that typically people do see this stuff. So I don't expect you guys to know every little thing about this, but the things I do want you to understand, do want you to get out of this, is this idea that energy is quantized. All energy, not just some energy, all energy is quantized. What do I mean by that? What do I mean when I say energy is quantized? Yeah, so it's not a continuous flow of energy, it's a continuous flow of packets of energy. Okay, it's not a stream of whatever amount of energy possible, it's given off in discrete units of energy called quantum, or quanta.
Like pouring sand, it's not a fluid. So
Sure, sure. Yep, you look at that. Okay? And those packets again are called quanta. The little packets of energy are called quanta. The process is called quantization. Okay? Secondly, electromagnetic radiation, which was previously thought to exhibit wave properties. That's what that one video was suggesting. That one guy said, hey, it's made up of waves, had some experiments to prove that it was made up of waves, and then along comes Einstein, and it seems that, oh, it also acts like a particle as well, and this led him to postulate that really energy is made up of both a wave and a particle at the same time, and he called that a photon. Okay? Seems to show certain characteristics of particle matter as well. The phenomenon is sometimes referred to as the dual nature of light, or the wave-particle duality. Okay, what's interesting here, I'll get to the last equation, the last problem here in a sec, is that in the end, all matter exhibits both particle and wave properties. What's interesting is he would argue that this desk acts as a particle and a wave at the same time. Okay, so let's wrap our mind around how this works. This is what Einstein said, is that very, very large pieces of matter, such as baseballs, basketballs, anything that relatively large, okay, tends to exhibit predominantly particle qualities. What do I mean by that?
It seems like it's
Yeah, it acts like a particle, like straight line motion.
like a thing.
Yep, straight line motion. When we think about bigger things, they predominantly exhibit almost all straight line motion, particle motion, very little what? Wave motion. Okay? Then very, very small bits of matter, such as photons, seem to exhibit predominantly wave patterns. And very little what pattern? Particle pattern. And guess what falls smack dab in the middle of that mass spectrum? The fun little electrons. And so electrons tend to exhibit both at the same time.
So what's smaller?
Like photons, like light. All right, we can't even really measure this. And this is where this idea that light has mass, but only if it's moving. It's weird to think about. Light, what they believe is light is actually just really, 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 really small bits of matter, smaller than an electron. Exactly. We've just started to figure out that there's subatomic particles.
Well, certain reactions release light. Where does that, if it's a mass, where does that mass come from?
Exactly. Good question. I'm not sure.
Like, what is it? Like,
I know, it's mind-blowing.
I
I think,
dead photons that get energy.
and again, we're talking really, I mean, this is first year college chemistry class, right? We've got all the way up through senior year, and probably some of this stuff really gets hit once you get in graduate school, or even you get in your doctorate. I mean, this is high level stuff that we're just dabbling in right now. Okay? Last thing here, I think this is the last problem, right? The only thing we haven't covered? Okay? So it says compare the wavelength for an electron. Okay, there's the mass of an electron traveling at a speed of 1.0 times 10 to the 7 meters per second with that of a ball with this mass traveling at that speed. Right? So let's figure out.
You underline the 9.11. That's bothers me. Thanks. Male.
Okay? So we know the mass of an electron. 9.11 times 10 to the negative 31 kilograms. So here we're going to see the difference between a really big particle and a really small particle. We have the mass of a, what is that, a bowling ball or just some ball? Just this ball. Okay, along with the velocity of that, moving much slower, it would make sense. Let's figure out and compare their wavelengths. Planck's constant, along with, so the equation we're going to be using here would be your wavelength is Planck's constant divided by your mass times velocity. Okay, 6.626, is that right? Times 10 to the negative 31 joules times a second. Mass, we know, is really small. And velocity is really large. Almost done here. one has a wavelength. What was that? No, because a joule is really a Newton chimes a second, and a Newton has a kilogram in it. So it cancels out the kilograms and the newtons. I think it might be a Newton per second. I can't remember off the top of my head. It's a Newton something second. 1.9 times 10 to the. Now, this is just all speculation here, but if you look at the electron, it appears to be doing much more frequent. And a ball kind of tends to act like that. And I know this is probably not how it works, okay? But if I sped this up enough, wouldn't it kind of just look like that?
Yeah.
Okay? I don't know. I'm not 100% sure exactly how this works, but I think it's pretty interesting. Now what you see here is the bigger the object, the longer the wavelength. And the smaller the object, the closer and quicker its wavelength, or its frequency is, and therefore.
Most of the time in the middle.
What was that?
It was a straight line. It spends most of the time in the middle.
Okay,
Going
so
up
you can
and
see
down.
how maybe it could act like a wave and a photon at the same time. And this is, if you get this really extended out, it kind of just looks like a straight line too, right? I'm not sure if that's exactly how that works, but I mean, it's interesting to think about. All right, I know you guys' heads probably hurt a little bit.